Okay, this is to go through the last 4 free response problems from your test. I'm going to go fairly quickly but explain each part. I'm going to try to. Okay. So, for question number 3, the temperature in degrees Celsius of an oven being heated is modeled by an increasing differentiable function h of time t, where t is measured in minutes. The table above gives the temperature as recorded every 4 minutes over a 16-minute period. For A, we're supposed to use the data to estimate, that's the key word there, the instantaneous rate at which the temperature of the oven is changing at time t equals 10. Show the computations that lead to your answer, indicate units of measure. So, since 10 is between 2 values that we have, that's why we have to estimate. So we're going to use the average rate of change formula to estimate, and this will be A, h prime of 10. So you find h of 12, and we're going to subtract h of 8 divided by 12 minus 8. If you do that, 80 minus 73 over 4, so you get 7/4. Now, the key here is to make sure that you indicate units of measure, because you do get your answer point based on that. So it'll be degrees Celsius per minute. So that's the average rate of change, or the estimate of the instantaneous rate of change at 10. For B, we're supposed to write an integral expression in terms of H for the average temperature of the oven between time equals 0 and time equals 16. Estimate the average temperature of the oven using a left Riemann sum with 4 subintervals of equal length. Show the computations that lead to your answer. Okay, so we're supposed to just write an integral expression between 0 and 16 of the average temperature. So that's where you have the B minus A situation going out in front. And we don't know what h of t is, but this will calculate the average temperature of the oven between 0 and 16. So you write that. And then to approximate it, you're going to use a left Riemann sum, because remember, Riemann sums give you an estimate of the area underneath the curve, which is integration. So here we go. I think let's just do from 0 to 16. So from 0 to 16 of h of t dt, the Riemann sum is basically finding the areas of rectangles. It wants us to have equal width, which it already has equal widths of 4. So my change in x here is going to be 4. And then all of my y values, this is like length times width. 4 is my width, and my length is given by the left-hand values here. So this is the left-hand value of the first rectangle. For my height, this is the next left-hand rectangle for my height, and then for 73 and 80. And we leave 90 off because that would be the right-hand side of the last rectangle there. Adding all those up gives me 286. And then the average temperature is going to be this times this, all divided by 16, or multiplied by 1 over 16th if you want to write it like that. And then punching that on a calculator gives me 71.5 degrees Celsius. Okay. So far we've earned 5 points, just so you know. For C, is your approximation in part B an underestimate or an overestimate of the average temperature, and give a reason for your answer? Okay, we're going to say that the left Riemann sum is an underestimate of the integral, We know this is an underestimate because the y values keep increasing in your table, which means whatever this function looks like, it's going to be increasing. And so when you draw in rectangles where the left-hand side is what you're basing your height of your rectangle on, it's all going to be underneath that curve. So the left Riemann sum is an underestimate of the integral, and my reason is because the graph of h is increasing. And then my approximation, so this is just talking about the left Riemann sum, but my approximation was the average. Okay, 71.5 degrees Celsius is still an underestimate. Since dividing by 16 doesn't change the graph. We should say underestimate of the average temp. So identify what's an underestimate of. Okay, and then part D. Question, are the data in the table consistent with or do they contradict the claim that the temperature of the oven is increasing at an increasing rate, and give a reason for your answer. Okay, so we need to consider a couple things here. Okay, so if we have a continuous function, is increasing at an increasing rate, then the slopes of the graph of the function are increasing. Okay, so basically what we're going to do is we're going to find the derivative, and if you notice, or the average derivative, you're finding the slopes. And if the slope values go up, then you can say, yes, I'm increasing at an increasing rate. My slope values are getting bigger. So we've already found the 7/4. So the slopes of the four secant lines, we'd have to do h of 4 minus h of 0 all over 4 minus 0. If I do that, I end up getting 3/4. I already got 7/4 in part A. And then we'd have to do it between 8 and 4. So h of 8 minus h of 4 all over 8 minus 4, that gives me 5/4. The last one, h of 16 minus h of 12 over 16 minus 12, that ends up giving me 10/4. Okay, so it is important to consider all three because you have to see that they're increasing. You go from 3/4 to 5/4 to 7/4 to 10/4. Yes, you are getting bigger. So since the slopes are increasing, the data are consistent with the claim. Okay. When you're ready, go ahead and flip. Alright, let f be the function given by f of x equals ln x sine x. The graph above, I feel like we already did this one. Oh, no we didn't. Sorry. Alright, so we're going to find g of 1 and g prime of 1. And g is defined as g of x equals the integral from 1 to x of f of t dt. Now, just because it's written there where the function of x is the upper bound, that doesn't automatically mean you use the second fundamental theorem of calculus. You're only going to use that when you take the derivative. So when we find g of 1, that's just plugging 1 in for x. So from 1 to 1. We don't know what, well, do we? Oh, this is non-calculator, so you do have to be careful. That's going to end up being 0 if you look at it that way. So if we plug 1 in for x, and then evaluate it, whatever the integral of f of t is, f of 1 minus f of 1 would give you 0. Because you're subtracting it from itself. G prime of 1, however, is the second fundamental theorem. So that's taking x and plugging it in, and then taking the derivative. So g prime of 1 would equal f of x, or f of 1, because g prime would be f of x because you plug the upper bound in and then multiply by 1, which is the derivative of the upper bound. So you get this, and then they want you to plug in 1. So f of 1 is what you get when you plug in 1 into that function. And there you end up getting 0 as well, because sine of 1, or maybe it's ln of 1. ln of 1, yes, ln of 1 is 0. So you end up getting 0 again. Okay, for B. On what intervals, if any, is g increasing, and justify your answer? This original function or original graph is the graph of f, and we want to see where the graph of g is increasing. And graph of g is the integral of that function. So, since g prime equals f of x, okay, so since g prime, since this is the derivative, and maybe we need to write that as well. This is also the derivative of g prime of x. Or sorry, this is also the graph of g prime. We don't know what g is. We just have a description for it. If this is the derivative graph, I know the original function is increasing wherever the derivative is positive. So it's going to be between 1 and pi. So, since g prime of x equals f of x, g is increasing where f of x is greater than 0. And then we have to identify the interval. We said from 1 to pi. Okay. For C, for 0 to 2 pi, find the value of x at which g has an absolute minimum and justify your answer. Okay, so here we go. For 0 to 2 pi, g prime of x, because we're looking for the absolute minimums, we have to find the relative minimums of g, which you find by taking the derivative and setting it equal to 0. So g prime is equal to f of x, which is this function, so they're all kind of equal. And the reason I have to state this is because I'm going to use this to find the points where there's possible maxes or mins. So it equals 0 when x equals 1, pi, and 2 pi. G prime, or the function f, changes from negative to positive only at, so from negative to positive, that would be a minimum, where you're decreasing and then increasing, only at 1. So we would say that the absolute minimum must occur at either x equals 1 or the right endpoint. And the reason it has to be the right endpoint is it can't be here, because you can clearly see that it decreases a lot more over here. So you could probably have a lower value since there's so much more decreasing here. And you did increase and then decrease again. That's why we don't have to worry about the left endpoint. We just have to worry about the right endpoint. Okay. Now to figure out what the right endpoint is. Since g of 1 equals 0, that's something we found at the very beginning, that g of 1 equals 0. Oh, you know what? I already said that, but yeah, we're going to have to, sorry, I'm looking at my other notes here. Since g of 1 equals 0, and g of 2 pi, so look, we're accumulating value here, because remember this is g prime, so when I say g of 2 pi, that's talking about accumulating value here. G of 2 pi is equal to 1 to pi of that function, pi to 2 pi of that function. Okay, and the reason I split it up into two areas is because I know that g of 1 equals 0, and then there's increasing from that point to pi, and then decreasing. So I'm adding up the positive area and the negative area, because the positive area is so much less than the bigger area. I mean, I can't find those areas. But because the comparison of the two areas, this one's smaller than this one, you're going to be increasing a heck of a lot more than you're going to be decreasing a heck of a lot more than you're going to be increasing. We would say that this here, g of 2 pi, is going to be less than 0 by comparison of the two areas. Now, the only other option, remember, would have been that the absolute minimum must occur at 1, but I already know the value at 1 is 0. That's what I got here. So this, obviously, you increased and then you decreased a heck of a lot more. The right endpoint is going to be the absolute minimum. Okay, so let me just walk you through that again. You look at the graph, recognize this is the derivative graph of the original function. So because the derivative changes negative, positive only once here, that's a relative minimum. But then I also have to check the right endpoint here, because I can see that I increase and then decrease again. So I might be lower in my original function here, because I might have decreased further than this. In the very beginning, you found g of 1 was 0 in part A. So we know that if that's a minimum, then my minimum y value is 0 there. And then you increase, and then you decrease, and because this area you increase is not as big as this area that you decrease, that gives you an absolute minimum at 2 pi, because if they were equal, then you'd be back at 0. But since they're not equal, you decrease below 0. Okay, and then for D, for 0 to 2 pi is there a value of x at which the graph of g is tangent to the x-axis. Explain explain why or why not. And we would say, yes, the graph of G is tangent to the x-axis, and the reason being, my first step here, when I plugged in 1, I got 0. That's on the x-axis. But then G prime of 1 was also 0, which is the slope of the tangent line. And so it's at x equals 1, since G of 1 is 0 and G prime of 1 is 0. That's all you have to say there. Okay, go ahead and flip. Two more to go through here. Okay, consider the differential equation. dy over dx equals x over y. The slope field for the given differential equation is shown below. Sketch the solution curve that passes through the point 3, negative 1, and sketch the solution curve that passes through the point 1, 2. Okay, so 3, negative 1 is here. To sketch the solution, you just kind of follow the slopes, okay? So that would be solution curve there, and then maybe that's the solution curve there. Okay, just for that first part, you got 2 answers. Okay. Oh, you know what? I made a boo-boo here. That part shouldn't be there, because I didn't notice that we didn't have any slope field or many slopes there, which means this is an asymptote. And so I would need an open circle there, and then just to go down. Okay. For B, write an equation for the line tangent to the solution curve that passes through the point 1, 2. So this is taking your function dy over dx, x over y, and then I get my x's, my y's, my y's. So y dy equals x dx, and then we're going to integrate both sides. So you get 1/2 y squared equals 1/2 x squared plus c. And then we need it to pass through the point 1, 2. So it's plugging 2 in for y and 1 in for x. Solving for c. So this is 4, this is 2. This is 1/2. So subtracting, so you get 1.5 equals c. Or well, does it say? Oh, goodness graciousness. Whoops. I did not read that. I'm doing part C here. Sorry. Part B, write an equation for the line tangent. Okay. So, sorry. This is going to be part C. We'll come back to it. Part B, I know. Okay. So, sorry, that's just plugging 1 in for x and 2 in for y to get your derivative. Okay. And So y minus 2 equals 1/2 times x minus 1. So that's your equation of your tangent line. And then back to part C, find a particular solution to the differential equation with the initial condition 3, -1. So actually, I'm going to have to back it up right there. So you do this whole thing, and then when you get to here to solve for C, you're going to plug -1 in for y, and 3 in for x. And so you get 1/2 equals, this is 9/2. So subtract 9/2, which would give me -8/2, which is -4. Right? How it says, sorry. Oh, let's see what they've done. Yeah, we can do it this way. So -4 equals your C, so you'd plug that back in. 1/2 y squared equals 1/2 x squared plus or -4. Then you multiply everything by 2, and then take the square root. Okay. Now for the domain, because this graph right here, and the reason we had to go the lower end of the graph is because your point was on the lower part of that graph. Because it extends this way, we have to take the negative, because remember when you take over the square root of both sides, you end up getting positive or negative. You have to take the negative. And then the domain here would be for x values that are greater than the square root of 8. Because if we were to plug in the square root of 8 here, really what you're doing there is you're saying, okay, what makes that 0 underneath? Because I can't go up less than that. And so you'd get the square root of 8. Okay. And then last one for 6. Let g of x be that function where b is a positive constant. Find the limit as x approaches infinity of g of x. Now, in this case, since we can't use a calculator, you have to think about what that means. As x approaches infinity, that's when x is getting bigger and bigger and bigger. So as x gets bigger and bigger and bigger, with negative exponents, that's really a fraction. So you could look at that as x over e to the x plus b over e to the x. So as that value gets larger and larger and larger and larger, and I know x is here, but that's going to be a much bigger value because it's 2.7 raised to that power. You're going to get closer and closer and closer, because if that gets bigger, then really that fraction is getting smaller and smaller. You're going to get closer and closer and closer to 0. You're never going to get to 0 because it said b is a positive constant. So you're always going to be adding positives together. So you might get really close, but you're never going to actually get to 0. And then for b, for what positive value of b does g have an absolute maximum at x equals 2/3, and justify your answer. So we have to find g prime, because if we're looking for a maximum, then we have to look at the derivative and see where my relative maximums are. We have to use the product rule here. So you have the derivative of the first times the second plus the first times the derivative of the second, which derivative of e to the negative x is e to the negative x times -1. And then the same thing here, except that b is just a constant, so it'd be plus negative b e to the negative x. Okay, so there's my derivative. And I'm going to factor out my e to the negative x here. So I get 1 minus x minus b. And then I'm going to see what g prime of 2/3 is for this. So I'm plugging 2/3 for x. You get 1 minus 2/3 minus b times e to the negative 2/3. I'm going to take that, set it equal to 0, because I'm trying to find my max or my min here. And so by doing that, I would get, well, we might just be able to look at this in a hypothetical manner. And this is going to be some fraction. But in order to get this equal to 0, b would have to be 1/3 in order for g prime of 2/3 to be equal to 0. Okay? And they would say for x less than 2/3, g prime of x would be greater than 0. And I would know that because if it's less than 2/3, so 1/3 or, well, let's go less than 1/3, I guess. If it was 0, then that would be a fraction. It's not a negative number, it would be a fraction, but what's inside the parentheses would be positive. So we would say our derivative would be positive. And for, sorry, I just looked at the time. For x less than 2/3, your derivative is greater than 0. And then for x greater than 2/3, g prime of x would be less than 0. Again, because if this is a bigger value, then inside parentheses there you'd have a negative number. The reason we have to make this statement here is because we have to show that the derivative changes at 2/3. So we show where it's equal to 0, which is at 1/3. That's my critical value. Then I have to show it changes from increasing to decreasing, or positive to negative. And then we can say, therefore, when b equals 1/3, g has an absolute maximum at x equals 2/3. Okay, and then for part C, find all values of b, if any, for which the graph of g has the point of inflection on the interval from 0 to infinity. Justify your answer. So now we have to take the double derivative here because we're looking for points of inflection. So looking back up here at this section, we have negative e to the negative x plus derivative of the first, which is negative 1, plus first times the derivative of the second, plus b to the e. Okay, and then again I'm going to pull out e to the negative x. So we get negative 1. Oh, we have two negative 1s, so really that's negative 2 plus x plus b. Okay, there's my second derivative. Okay, and then you look at the expression inside the parentheses again. If your b, we can see if it was 2, I'd be equal to 0, so that's a possible point of inflection. But if your b is between 0 and 2, let's think about what happens there. If it's a 1, is it giving me a value here? Oh, no. Sorry. If b is between 0 and 2, Then G double prime will change sign at x equals 2 minus b, oops, greater than 0. Okay, so that's taking 2, subtracting b. It's just basically saying that that expression there is going to be greater than 0. And then we can state, well, let's dive into this a little bit more. If your base is between 0 and 2, or sorry, your b value, this is still a fraction, whatever x is. X can be any positive number between 0 and infinity, so we know that's going to be positive. So really you're just looking to see, okay, let's say x was small. X is 1. Okay, b has to be bigger than that in order to make that a positive value here, or to change concavity. So we need it to change sign somewhere. So we're saying, okay, if that b is between 0 and 2, taking out the x and just worrying about the b, then it'll change sign at 2 minus b greater than 0. So as long as you take 2 and subtract whatever your b is, and it's bigger than 0, you're going to have a point of inflection there. So therefore, the graph will have a point of inflection on the interval 0 to infinity when your base is between 0 and 2. I keep saying base, sorry. I mean b is between 0 and 2. I know this part is confusing here. I'm trying to think if there's a better way to write that. But it's probably the best way to write it. As long as you can take that 2 and subtract b and still be bigger than 0, then you're going to have a sign change. Okay. Now, that last problem is a doozy. Okay, that's not typical. That kind of problem is not typical. They probably threw that in there as a review of like how to find absolute maxes and mins and points of inflection. But the other 5 we have practiced quite a bit, so you should be able to handle those pretty okay. So don't stress out about this problem. Okay, spend your time between today and tomorrow just looking over your notes, practicing some stuff, looking at free response problems online, doing whatever. Don't stress out. You guys will do fine.